Our next talk in this session is by Ulla Svensson from EPFL. His broad interests are in algorithms with a focus on combinatorial optimization, and recently how to use ML to improve performance. And his talk will be on learning-augmented online algorithms and the Primal-Dual method.
Okay, thank you very much. It's a pleasure to be here. So this is joint work with two of my students at Jan Bamas and Andreas Maggiori. So yes, as Ronit said, I will talk about learning-augmented online algorithms. So I will spend some time introducing them. Then we'll see a case study of one of our favorite problems in combinatorial optimization, set cover, and we'll see. I will cover a classic way of designing online algorithms for this problem using the Primal-Dual method. And I hope I'm able to describe this method so that it will become pretty natural to incorporate predictions, and this will give us a framework for using the Primal-Dual method to incorporate predictions that we'll see for other problems. All right, so let's start with online algorithms. And Sagi was already kind enough to describe my example. So, suppose you go to Google, you search best graduate school, then you have some patience, you get your responses, right? And they make perfect sense, except maybe, the first reply is a little bit weird. What kind of school is that? And that was, of course, assigned by an allocation algorithm to maximize some profit, I suppose. So more, abstract, maybe you have some advertisers and you get searches arriving online. When a search arrives online, you have to irrevocably decide which ad to display on this page. Maybe only one ad per page. So maybe Pepsi, Thirsty. Rivella is like the Swiss version of Coke and Pepsi. It's an acquired taste. If you come to Switzerland, it's a nice taste. Okay, so there's Rivella, and then maybe someone is interested in furniture, it's Scientific and so on. So the point is that the instance arrives online, but we have to make irrevocable decisions before we know the whole instance. So that's kind of the difficulty of online algorithms, is that we do not know of the future. And in theoretical computer science, we have traditionally measured the performance of these algorithms in terms of the competitive ratio. So an online algorithm is C-competitive if for any input sequence, it finds a solution that has value at most C times opt if minimization. So here you want C to be as small constant as possible above 1, and at least C times opt if maximization. So just to get a little bit comfortable here, if you haven't seen on this way of thinking of online algorithms, the classic example is relevant also in Switzerland. So it's called the ski rental problem. And the problem is that it costs you $B to buy skis, but you can rent skis for $1 a day. And the unknown variable is the number of days you will be skiing. Okay, because who knows? Bad weather, you may injure yourself and so on. So now what should you do? So what's a good strategy here? So you don't want to buy the first day because maybe you figure that skiing is not for you. So then you paid $B, whereas the optimum only paid 1. And you don't want to rent for the rest of your life if you're going to ski way more than B days. So a reasonable strategy turns out to be, I rent for B minus 1 days, let's say. And then if I want to ski more, I actually buy at day B. So why is this a reasonable strategy? Because if you turn out to ski less than B days, this is optimal. You should have rented to start with. And if you ski more than B days, well, you paid 2B, but the optimum paid at least B. So this is as a competitive ratio of 2. Okay, and this turns out to be the optimal competitive ratio if you have deterministic algorithms, and E over E minus 1 is better if you use randomization. All right, if we come back to the ad allocation example, it turns out that the greedy gives you 1/2, and if you allow yourself to use randomization, there's a beautiful ranking algorithm by Fazzani from 1990 that is 1 minus 1 over E competitive. So maybe like this is for the matching question. If you look at the ad allocation question that Sagi talked about, when you have a B matching, there are much better algorithms when you make assumptions that the budget is much more than the cost of displaying one ad and so on. This has been heavily studied. I just focused on the matching question here. So now if you have a big company, maybe you're not happy with a 0.67 guarantee, and maybe one reason is that the definition of this competitive ratio is for any input sequence which may be a little bit pessimistic. So to make the case that this may be pessimistic, I have, this is actually stats from Google. So this is the search stats for Premier League in the UK. So, they don't look impossible to predict. So this is Sundays. So this when there is a game. Okay, so maybe we can use some predictions to improve our algorithm. Okay, so I don't know much about ML algorithms, but I know that they have excellent guarantees normal days, but they often they seldom come with worst case guarantees. So maybe you get crazy one day and you don't even return a matching. Who knows? Okay, so and to make the case that sometimes it's good to have worst case guarantees, I didn't fake this graph. Actually, this is actually what happens in real life. If I extrapolate one more week, you see this weird behavior. So there's one Sunday when the British people decided that they should not search Premier League for some reason. So that's the true graph here. Anyone can guess why they didn't search Premier League one Sunday? No, Ronit, you have to answer because you're the only one. Maybe you're not interested in football.
Was it Easter?
Yeah, well, it was actually the World Cup qualifying games.
Okay.
So it was not impossible probably to predict, but it's not easy. Okay, so this brings us to learning augmented online algorithms. Basically, we want to combine the good things. So online algorithms, they have very good worst case guarantees, but perhaps not the best guarantees in typical instance.
Ulla, there's a question.
Okay.
Philippe is asking, is this the 1 - 1 over E of submodular optimization? That was probably back a while ago and I probably missed it.
Oh, I see. No.
Yeah.
No, I don't think they're related, no. So in fact, actually the algorithm is the greedy, but they have a random permutation of the vertices, to which then they go through that list greedily. The analysis is tricky, much more tricky than for submodular functions and much more delicate. So that's why there was many references. I think the most beautiful analysis I know is like a dual fitting argument by I don't know all the authors, but by Nikhil Devanur and others. So yeah, you could believe, but I don't know if there is some smart relationship. I cannot promise you, but I don't see it now. Good question. Okay, so was there any more? No. So then ML, no worst case guarantees, but good in typical. So we want learning augmented algorithms to have the best of the two worlds. Okay. So basically, it's an online algorithm that is augmented about predictions about the future. And the question is, how well can we use those predictions about the future? And kind of the tricky part here is that we may want to make no assumptions on the predictor. We don't understand the predictor at all. So without making any assumptions about a predictor, how can we use it? So then there's like 3 desiderata that we would like our algorithm to have, and that is you have seen it in Sage's talk, right, with the Hungarian method, and maybe not in Woodruff's talk, David's talk so much, but he only had the consistency case. But here we would like that if predictions are correct, then algorithms always gives a good solution. So we want somehow use the predictions. If they're good, we want our solutions to be good. But at the same time, we want to maintain some robustness. So even if the predictions go completely crazy, even adversarially, then we would like to maintain the worst case guarantees that we like from online algorithms. And yes, you would like the smoothness, meaning that if the predictor is slightly off, you still want a good guarantee. But for the purpose of this talk, I will just not discuss this because we only have 40 minutes. Okay, so that's our goal. We want to design algorithms that if the predictions are good, then we get a very good solution, and we want to maintain our robustness. So the best of two worlds. Of course, I didn't come up, no, I want to, before I say I didn't come up with this, let me give you an example. Let's go back to ski rental. Right, so now we have the same ski rental problem, but now I also give you a prediction. like I can look at Philip. He will only ski 2 days next season. So no, but you get the sorry, Philip. So prediction P of the number of days you're gonna ski this next season, and now you have to make your choice. And now we want to be good if the prediction is correct, but we don't want to be arbitrarily bad if it is crazy. So you could, of course, if you don't trust the predictor at all, just run the online algorithm, but then you have bad consistency. You don't get a good solution if the prediction is correct. And if you completely trust the predictor, you know, things can go very bad. Suppose the prediction says that you should ski 10 B days, so you buy the first day, but then you only ski 1 day. So you are like B factor away from the optimal, so bad robustness. So it turns out that there's an interesting trade-off between how much you should trust the predictions and how good robustness and consistency you can have. And for ski rental, if you think about it for a while, you realize that you should actually wait lambda B days to buy if the predictor says that you should buy. And lambda is this trust parameter. And this would guarantee you consistency 1 plus lambda if it's correct and 1 over lambda if it's bad. Okay. So this is just to make a case that for many precedents, actually, it's not trivial. You cannot just follow predictors. You have to do something clever. And this, yes, I didn't. So you can actually be traced back on the ad allocation setting by Mariana Sade and Saberi. And more recently, you know, and the reason like I got to start work on this was a great paper by Lukoris and Sergey, who did competitive caching and introduced this learning-augmented setting. And you know, since then there has been tons of works and courses, and I guess I don't have to say workshops because we are in one. So all right. So then we were looking at this beautiful book, monologue by Buchbinder and Nauer on how to design online algorithms using the Primal-Dual approach. And then we asked ourselves, can we adapt? So this is a very powerful framework for online algorithms. So that works for many different problems. And now the question is, can we adapt this approach to incorporate predictions and then maybe hammer down many questions with one approach? Okay, so then I want to introduce this framework of devising online algorithms using the Primal-Dual method. And I hope I will do it in a way so that we will see how to incorporate predictions. And we will do so by looking at what's called the online set cover or fractional online set cover question. So what is this question? What is this question? So we have a number of elements. No, we have a number of sets. So here I have 2 sets. And then elements arrive online. So think of these blue stars as potential elements that could arrive online. We don't know them. They will arrive online. Okay. And when an element arrives, we need to fractionally cover it using the sets. Okay, and we want to minimize the sum of fractionally selected sets. So let me make the example and it might make sense. All right, so suppose this yellow star arrives. We need to fractionally cover it, and it can be covered by either set S1 or S2. Okay, so one fractional coverage of this element is to put both sets to be 1/2. Okay, so this is the constraint. I need to cover this element, so I need to cover it with S1 or S2. I can put each one to be 1/2, and I have covered this element fractionally. Now another element arrives, this one, it can only be covered by S2. Now my decisions are revocable, which means in this setting that I'm not allowed to lower variables that I already increased. So I can only push up. I can monotonically increase the size, the fraction I selected as set. So now I need to cover this element, so I need to pick S2. So that's my new constraint, so I need to increase it to 1. So this gives me a fractional coverage of these 2 elements. The first element that can be covered S1 and S2, and the second element at S2. My fractional coverage the fractional coverage that I did online had value 1.5 and opt had value 1. Okay, so here I was free-house competitive. So this is a nice question that you know generalizes many other questions. It's like, of course, it's maybe you don't see any applications immediately, but it's a clean question to start our study on. Okay, any questions about the problem? Okay, so let's just give me some intuition here, so let's look at the difficult instance. So I have m sets, S1 to Sm. The first element that arrives can be covered by all elements. So what are you supposed to do? Well, you know nothing about the future, so you may as well set the coverage of these sets to be equal, 1 over m. So any reasonable algorithm would do, let's say. So 1 over m on every set. It covers this element with at least 1. But now I give you a new element that can be covered by all but the first set. So what are you supposed to do? I don't know anything about the future, so I just increase these m-1 elements. So I will put them to 1 over m-1, and so on. Okay, and you will see that I will get a solution where the first one is 1 over m, the second is 1 over m-2, 1 over m-2, and this is 1. So this will be the harmonic number log m. And this turns out that in fact any, so of this one, so it's log m competitive, but any online algorithm cannot do better than log m just by massaging this example. So log m is the best you can do if you know nothing about the future. And we will see how to beat this using predictions, okay, for this and other problems. And just, to make clear that predictions, you cannot just use them trivially. So suppose you have a prediction, say, hey, you should cover this element using SM. Okay, so let's put SM to be 1. And then, of course, I'm very happy for this instance because I got a 1. But if I completely trust the predictor, of course, if the predictor is bad, he will predict that I take S1, I take S1, then I need to take S2. A predictor could fool me to pay M if I completely trust the predictor. So that's just that we say that we have to do something smart here to do something to maintain worst case guarantees. Okay, completely trusted predictor has terrible robustness. So there's some interesting trade-off to be got.
Ola, I missed it. Is there an algorithm that achieves O of log m in the worst
Yes,
case?
I will give it now.
Okay.
Very good question. So this is like the Primal-Dual approach. So remember, we have elements arriving that should be covered. Okay, so for every element, we should cover them by the sets that contain this element. And then we want to minimize the total amount of sets that we picked. So now, no one will understand, but if you do write down the dual, so also I have the non-negativity, I didn't write that. So if you write down the dual, it would be a packing LP. Forget about the dual at the moment, it's not important. So now we want to devise an algorithm for this question. So we start initially, x is equal to 0. We haven't started, no element has arrived, so no set has a fractional value. So now at arrival, element E, what should we do? So if the sum of I, E is in Si, X Si is greater than 1, there's nothing to do, the element is already covered, so we are super happy. Okay, so do nothing. Else, we need to do something, right? So the element is not covered by a current solution. So what should we do? So now we need to update them. So for each Si such that E is in Si, so for each set that covers E, we update it. All right, so I think of the initial starting set. We have an element that arrived, E, that could be covered by, say, 3 sets, S1, S2, S3. We know nothing about the future, so we may as well just set these sets to be 1 over the number of sets that cover E. So we will just set this 1 over number of sets covering E. Okay. And then we will also 2 times XSI plus, okay? So this here guarantees that we cover the element because, we will increase that many sets by 1 over the number of sets covering E. And then this 2 times XSI will make sure that we get a good worst case guarantee. Okay, so that's our whole algorithm. And then for bookkeeping purposes, I will also increase Y to set it to be 1 for elements where I needed to do some updating of the primal. All right, so that's my algorithm. So upon arrival of a new primal constraint and the corresponding dual variable YE, If it's not covered, then for each set that covers this element, update it by taking twice the old value plus 1 over the number of sets covering E. So in the example, we have an element, first 3 sets come. You know, this set, we have all the x variables to 0, so this element is not covered. So we will set them to be 1 over the number of sets covering that element. So we set them to be 1 over 3, all of them. Then a new element comes. It's not covered because xs1 plus xs3 is less than 1. It's 2/3. So we need to update them. And if you do the calculations, they will be set to be 7 over 6. I'm a little bit wasteful here. You would probably not want to increase variables more than 1, but let's forget about that. Okay. And if you know this guy comes later on, you're happy because he's covered, so you don't do anything. Okay, so now we will analyze, and I will show you to the, so this is basically the first chapter in their book. So let's prove that this is a log M competitive algorithm. So first, when we update the primal, how much do we increase it with? Okay, so when we update the primal, how much do we increase it with? So what is the delta x? Delta x is equal to sum of xsi I such that E is in Si plus 1 over the number of sets covering E. Okay. But this sum here ranges over all the sets that can cover E. So this here will become exactly 1 in this sum. And this sum of xsi, well, we updated it because it was less than 1. So this whole sum here is at most 2. So every time we update the primal variables, the primal increases by at most 2, actually strictly less than 2. And at that point of time, we also increase the dual by 1. Okay, so as each step, the increase of primal is at most 2, whereas the increase in dual is 1. Now, it remains to prove that y scaled down by log m forms a feasible solution. Okay, because then by weak duality, we have that the primal solution is within a factor log m of the dual solution. Okay, so how do we prove that? So we fix a set Si. So fix a set Si. We need to prove this for a constraint. So for Si, need to prove that sum of E Si ye is at most log m. So why is that the case? Because every time we increase one ye in this constraint, we double xsi, right? We double xsi every time we increase a ye that it could cover. So if we look at this set xsi, every time an element arrives that is not so far covered, we double the variable xsi. But it started with a value of 1 over m, so you can double at most log m times until it reaches a value of 1. Okay, so that's the whole argument. So it's updating a constraint. The variable xi is double in primal. We can happen at most log m times as its starting value is 1 over m. Okay, so if you lost me there, that's the whole analysis, but I understand maybe someone lost me, and that's not serious. So now, of course, feel free to ask questions, but if you lost me, you can come back, because now we're going to go back to the high level, and hopefully I will make this point clear even if you didn't understand the proof. All right, so what happened in this algorithm? So when an element arrived, we had nothing, no knowledge about the future. So we set the probability, or we set the fractional value of each set to cover this element to be equal. We set everybody to be 1/4 in this case, because each one is equally likely to be useful in the future. So now suppose you have a prediction telling you that, hey, S3 is the perfect set. It's part of the optimal solution. What should you do? You shouldn't set the fractional value of all these guys to be the same, right? Because now you have knowledge about the future, so you should be more aggressive in putting the set that the predictor tells you to pick. Okay, and that's what we do. So instead of just setting it uniformly, we set, basically we put it to be 1 minus lambda for the guys that the predictor tells us to use, and lambda for the ones that it's not. So let's just think about this. So here, if the predictor says that S3 should be used to cover this set, then we will put it to be value 1 minus lambda plus lambda over 4. and everybody else for lambda over 4. So if lambda is equal to 1, we get back the algorithm we had before that doesn't listen at all to the predictor. And if lambda is 0, we blindly trust the predictor. Okay.
Well, can I ask a question?
Of course.
So here the predictor is always spinning out a certain number of sets. That's what it's
Yeah, so
telling.
here, yeah, very good question. So I didn't say it. So here we assume that the predictor has given us a solution. So he tells us at the beginning of the game, these sets will cover all the coming elements.
Okay.
Which,
and
you know.
What if, so it seems that this would be easy to adapt if the predictor was giving you a whole probability distribution vector on the potential sets that you get, right?
I think so.
Okay.
I have to think that would be a fractional solution. Yeah, I agree. Yes, probably. I don't want to make a, it sounds reasonable. I could maybe, yeah. So now analysis and guarantees. So good prediction, you can prove that this is 1 over 1 minus lambda competitive. This is very easy because you increase the variables that the predictor says very aggressively if lambda is close to 0. And at the same time, you get log m over lambda competitive. So this is exactly the same proof as I failed to explain in a couple of slides ago. Okay, so this means that I can, in fact, if I set lambda to be 1 over 2, I basically lost nothing in the robustness, but I have a constant factor approximation when the predictor is good. All right, so that was for online set cover. And now we can think of the general recipe. Well, our general recipe is look at Buchbinder's book. But, you know, they look at your favorite question, formulate an Alpi relaxation, look at the Primal-Dual algorithm. Now, in order to incorporate predictions, you just need to tweak the rate at which you increase the primal variables to incorporate the predictions. And we'll see that this leads to simple, well, we hopefully.
Yeah. I have we have a question, and it comes from Sandeep. He's asking, why is the prediction model natural? That's what he's asking. Yeah.
Well, yeah, so it's a good question. I don't know if the prediction model is natural for set cover. I will see how we instantiate it now. Hopefully it will be more natural prediction models. Okay.
Yeah.
So it's a good question. I don't know natural prediction. I don't know how, you know. Yeah, I mean, yes, I guess the prediction then would be like if an element arrives, the predictor tells you a probability distribution over which sets it would think that you should use to cover this element. Then our algorithm would work. So that's the only prediction model I could think of for set cover, but maybe there is more natural ones. I don't know.
Okay, thanks.
Okay. So yeah, we will see it. We will see it for ski rental, and then there's a related problem called banker. So I will talk about ski rental and TCP acknowledgement now. Okay, so yeah, it's actually easy to implement. Okay, so let's instantiate this framework. So ski rental, so now you look at the Primal-Dual algorithm for ski rental. It looks crazy, so don't read it. But there's one place where you decide how to increase the primal variables. Okay, the rate, that's basically here. So once you stare at this for a while, you realize that's where I will decide how to increase the primal variables. And now what you do is to change this prediction, change this speed based on the prediction. Here, to come back to Sandeep's question, here the prediction model is the number of days you will ski. So if you predict that you will ski more than B days, then you're more aggressive in increasing the variables that correspond to buying. And otherwise, you're less aggressive in increasing these variables. And by doing this change, you will recover these guarantees, which is by the same results of Kuma et al. From 2018. And these turns out to be the optimal trade-off. Okay, so by implementing this Primal-Dual algorithm, by tweaking the rate at which you increase the primal variables in a very similar way as we did before. So this is basically you have this additive term that you change here based on this if-then else.
Oh, wait,
so that's it.
One more question from Ahmed Sadeghi. Is there a hardness gap between Learning-Augmented online LP covering problems and online convex covering problems?
So I don't know, because that's one of the future directions is, can I do something smart here for convex objectives. For example, we did another work on speed, setting the speed of a machine to schedule tasks. And there the objective function is convex because the energy you use is convex in the speed, like, you know, s squared or s cubed. And there are primal dual algorithms or dual fitting algorithms for those problems without predictions, but we were unable to incorporate predictions there so far in a natural way. But that's a good question, how to incorporate predictions in like a wider range of primal dual algorithms. And we only now managed to nail a subset of the problems in the even for linear objectives. But one we managed to get this is very important TCP acknowledgement problem. So what is this? So you have a server receives a stream of packets, and you need to acknowledge them. So now you can decide to send an acknowledgement right when you receive a package. That costs you something, or you can wait. So sorry, the animations disappeared in the PDF. But you can also wait to send an acknowledgement after you receive many packets. So then basically your objective function is that you have to pay the cost of an acknowledgement plus the cost of the delayed packets. So there's a trade-off that I can wait to send acknowledgement until I receive many packets, and then I only need to send fewer acknowledgements compared to sending one immediately. Okay. And here there's a primal dual algorithm. And again, if you stare at this for a while, you can identify where do they set the rate of increase of the primal variables. It turns out to be this. Let's now incorporate the predictions. And here, the prediction is the next time the algorithm will, the predictor tells you when you should send the acknowledgement next. Okay, which I think is a fairly natural predictor. And here you get the same guarantees. We don't know if they're optimal, but that's what you get. Okay. Yeah, so similar to Sergey, we managed to implement this, and you know, the results make sense. So here lambda is how much you should trust the predictor. So a low lambda means that you trust your predictor a lot. So this is good. So this replacement rate is basically how think about how correlated the input is to the prediction. So if it's 0, it's very, very correlated. So then you do very well, and then you gradually do worse. But you are not too bad even when it's completely uncorrelated. So you maintain some robustness guarantees. But this is synthetic instances. Okay. Yes, sorry. So yes, I think this unifies some of the previous result and allows us to give some new results. And the proofs are actually easy. You just redo the robustness proof that were used for the primal dual algorithms before, and the consistency comes from a shorting scheme. Yeah, so we don't get everything. So for example, we don't do packing constraints. We cannot recover this adduction setting. And this we already covered. What about non-linear objective functions, like convex objective functions? And there, like one example is, for example, speed scaling for energy minimization. One thing that I was a little bit interested in, or I've been interested, we're thinking about now actually. So it's it's what if you have to pay for the advice? So it's a little bit weird now, right? We wrote the paper like, hey, let's minimize energy using a predictor, but we don't take into account the energy to produce the prediction. Or, you know, so what if you're gonna ski, and you can get a prediction of the number of days you're gonna ski, but it's not for free? How should you use that prediction? So that's something that turns out actually to be kind of not straightforward. Thank you.
Thank you very much. So you had a ton of questions in the, oh, we have another question in the Q&A. And this one is asking from Ahmed, if we play a convex combination of the state-of-the-art worst case algorithm and another algorithm that fully follows the predictions, would the competitive ratio results be strictly worse than the PDLA framework?
If we make a convex combination of the state-of-the-art worst case algorithm and another algorithm that fully follows the predictions, would the confederate results be strictly worse than? So I don't know. I have to. That doesn't seem. So this relates to the question when are these predictions interesting? It's when it's not for free to switch between solutions. So for example, maybe for the set cover, if you make a convex combination, you know, if you look at the worst case algorithm, it may not even cover it covers an element by 1, but if you look at the convex combination, it only covers its half. So now your best case algorithm needs to cover that set. So you need to put a lot of fractional value. So if the prediction is bad, it will make you pay a lot. But now maybe in the set cover case, you could say, okay, but let me run the worst case algorithm that is forces to cover each set 1 over lambda, where lambda is your factor, you take that worst case out. Maybe that works, but it's not straightforward to combine them. But that's a good question. It would be, I hope, it would be an even better solution if you just combine them.
Great. Are there any other questions? Oh, we have a question. Sergey, go ahead.
I'd like to return the favor. So I guess, you know, we've been battling with this question of what makes a natural predictor for a long time. And so one way to do this is to say, well, if it's path learnable, it doesn't matter if it's natural because at least I can learn it. It's an open-ended question. What's your take on, like, is that a good idea? Is that a bad idea? How do we answer these questions in the future?
Yeah, so personally, I think there's 2 directions. One is what the one you say, which is like, let's define something we can learn. And then I was thinking like another natural way is to think for what things do there exist predictions? Let's say when you do like I'm more comfortable with scheduling here. I would expect that Google has predictions of the number of searches at each time of the day. And then the question is, how can I use those predictions to devise a good scheduling algorithm? I don't know if that's pack learnable or not, but I think that's a natural predictor that probably Google has. So I think there's 2 ways, right? One is to define some weird predictions, like I don't want, but let's say I want to learn the duals of a linear program. Probably no one has come up with that predictor unless they need to solve this problem. So then it's good if it's pack learnable. But I would expect that other quantities, there are pretty good predictions. And then it's cool if we can use them to devise our algorithm. So.
Okay, makes sense.
But then again, in this setup, you would need to know how good it is so that you can tune your lambda, for example, right?
Yeah.
So I think
you don't need to. You can put your lambda to start with. It depends on how good you need to be in the consistency and robustness. But yes, it makes sense to tweak your lambda.
In any one-shot setting you're going to come up with, it's going to be impossible to define what a good predictor is, right? I mean, you know, you're going to be able to judge whether it's good by just repeating, you know, using it and see how you're doing based on this, right? I mean, you cannot just, I mean, you'd have to learn how good it is. There's this notion in stats called Oracle inequalities, but they only work in and they're basically measuring how good you are compared to an Oracle, which does not know everything, but does know the truth through the lens of a particular algorithm or something like this. So that would be, for example, somebody would apply your algorithm with the optimally tuned lambda. But this is only in the context of, like, you know, repeated attempts at solving this problem.
Yeah, so I think here so in some sense the goodness of the predictor, as usually defined in Learning-Augmented, is like instance per instance. So let's say you have the caching question and you predict when the next page of this type will come or whatever. So then maybe an error of your predictor is the L1 norm of this instance. So it's like per instance, and it says per instance, if the predictor it might be a horrible predictor for most instances, but if it happens to be correct on this instance, you should use it to do better. So it's a little bit different probably than you meant that you are good on average, like with respect to some distribution.
So actually, I have a question which is not very scientific. I'm just curious. So if you're going to show that prediction improves performance, why do you start with something that already has a log competitive ratio and not just like some polynomial competitive ratio that would give you much more margin of improvement? Like, is there a particular reason why you went for the set cover as opposed to something that has a known polynomial competitive ratio than logarithmic?
So So we looked at coverage problems, and then it's set cover. Yes, if you look at packing problems, then you get into the polynomial territory. But we didn't manage to do something interesting there, but maybe in the future.
Okay.
So if you, yeah,
I mean,
guess that's it.
You could hope to get more drastic improvements. That's all I'm trying to say.
Thank you.
Okay, it looks like we are both over time and out of questions. So I want to thank Ulla again.